control problems at the end. Since we are interested in discrete solutions, I mean numerical solutions in this work, I will talk about Runge-Kutta scheme also. But of course, it will be a stochastic case. And by using this scheme, I'm going to obtain optimality conditions of our model problem. I will not give all details, but I will give a scheme for how we get optimality conditions by using Runge-Kutta methods. At the end, I will give some numerical results to show the efficiency and efficiency of the techniques, of course. So, in a continuous time market, we usually use capital T for the final time. I mean, it's usually denoted as time horizon. And we let YT be the investor wealth, of course, having consumption and portfolioization effects. In general, there are two traded assets. We usually use BT for denoting risk-free assets, and for the risky assets, we use ST. For a risk-free asset, if you want to calculate the option price at a time t, we use a differential equation as dBt is equal to R times Bt times dt. It is usually, it's actually an ordinary differential equation, as you see, of course. It's an initial value problem. Here, there is no risky term. When we have a stochastic effect, then we call such structures as risky assets. Here, WT is denoted as standard Brownian motion, and sigma is the volatility. Alpha is called drift term or expected return. And we have risky asset formulation as dSt is equal to St times alpha dt plus sigma dWt. So, for some financial cases, we face jump effects also. Risky asset can be formulated as dSt over St is equal to some terms times dt plus sigma dWt and some coefficient times dNt. Here, NT is called the Poisson process effect. And there are some meanings for coefficients. Let me discuss some of them. For example, lambda is called the jump intensity, and ZT is jump size factor. K is called the expected value of the jump size factor -1. It is called mean jump size. In this work, we will also consider a pure jump model. I mean, we omit the WT term, so there is no volatility term here. It is called as pure jump model. Also, as a summary, if we don't have no jumps, then we get classical Black-Scholes dynamics. Jump diffusion case, we have a compound Poisson process in the formulation. And after completing the formulation of a Merton jump diffusion model, I want to talk about how we face applications of such models in optimal control, especially for portfolio optimizations and asset allocations. We face such problems. Our goal is to decide how much wealth to place in risky assets versus safe assets over time. And we have an objective function. We usually maximize expected utility of terminal wealth. And we may have jump effect also. Asset prices may experience sudden jumps. Also, we may have some consumption problems, and we may want to decide how much to invest, how much to consume at each time. So I will give a formulation for stochastic optimal control. An optimal control problem is consists of a control and a state variable. We usually use U for the control case, control variable, and the function J is called objective functional to be minimized or maximized. It is also called cost functional. Since we have a stochastic case, then we are interested in minimizing or maximizing expected value of such function. And in this function, variables are ut and xt. Xt is our, here in general, xt is a variable where satisfying given differential equation. It may be an ordinary differential equation, stochastic, or partial differential equation. In our case, it is a stochastic differential equation. And for our case, I mean, jump diffusion, Merton jump diffusion equation, our state equation is denoted as dyt is equal to yt times deterministic part plus stochastic part plus jump part. Also, we will consider pure jump model. In this work, we omit dwt, I mean the stochastic case. So this is our formulation in our work. Here we have a function j to be minimized, and we have a Merton jump diffusion model. And here we use some short notations to get formulas easily. To solve such a problem, I mean, in order to get a solution of a stochastic control problem, we may use Hamilton-Jacobi-Bellman formula or dynamic programming I mean, or we can use other techniques, but the most popular of them is called the Hamilton-Jacobi-Bellman equation. Here, we define a value function v to be minimized. We take infimum of that function. And when we get the infimum of this function and take partial derivatives, we get optimality conditions. I mean, to solve an optimal control problem, we have to minimize a cost function. Also, we have to solve a stochastic differential equation. For that reason, we need some other extra relation between control and state variable and the cost function j. Hamiltonian is a choice for giving this relation between them. Hamiltonian function is defined as L is the function inside the, let me show you here, L is function inside the cost function, and we choose some new parameters, let me say P and Q in the Hamiltonian. Here P and Q are called as adjoint variables, and we get optimality conditions when we take derivatives of Hamiltonian with respect to variables u and y. So for a deterministic control problem, there is only one adjoint variable, let me say lambda or p. But if we have a stochastic case, there are some extra terms related to this parameter lambda. and it is calculated as a second order derivative with respect to x, and we call that parameter as q. So, as we all know, analytical solutions of a complicated ordinary differential equation is not easy, but a stochastic case is much more difficult. When we also consider a stochastic control case, it is very difficult to find analytical solutions of such problems, so that we are interested in numerical solutions. To solve an optimal control problem numerically, we have two directions. One of them is optimize, then discretize, and other one is discretize and optimize. In the first case, we obtain optimality conditions, and after getting all optimality system, we apply a discretization method, let me say an Euler method or a Runge-Kutta scheme, to get the discrete optimality system. Or we may use discretize and optimize. At first, we find the discrete form of the state equation and the cost function. Then, instead of applying Hamilton function in continuous form, we use the discrete form and we get discrete optimality conditions. There are also some advantages and disadvantages of both techniques, of course, but the old technique is more flexible than the other one. So that in this work, we will use discretize and optimize technique. As for discretization, we consider Runge-Kutta methods. Let me show you the deterministic case at first. Assume that you have an ordinary differential equation, y dot is equal to f, and we have an update step yk plus 1 is equal to yk plus some terms, delta t times some terms. Also, we have an intermediate stage, and yki is calculated as follows. Here, alpha I and aij are called weights of Runge-Kutta method. And we have a stochastic version. Here, we have also an update step and also intermediate states. It is very similar to the deterministic case. Instead of delta t, we also have delta w and delta n from the jump terms. We also have Runge-Kutta coefficients, weights, I mean. So let me show you the discrete form of our problem. We have a function j we defined at the beginning. This is the formulation of our problem, but this is the discrete form. I mean, we applied the Runge-Kutta discretization to our model. Now, we use some short notations, HKI, FKI, and new KI. Here we have also intermediate values, YK is calculated. And also there are some other different notations, capital F, capital H, and capital S, to get the formula easily. Now, for a discrete, to get discrete optimality conditions, someone may use a Lagrangian function or Hamiltonian function. There are some slightly differences between Lagrangian function and Hamiltonian function. They are related to each other, actually. Here, L is defined as expectation of the our discrete scheme. We take all equation at one side and set them to zero, but actually we use a spatial name for such system, and this is denoted as L. Here, to get the optimality conditions, we need to take derivatives of L with respect to variables, with respect to y, I mean the state variable, and control u. Here, I'm omitting proof because it's very long. We set partial derivatives to 0, and we get the following system. We get a similar discretization, discrete scheme for adjoint variable also. And the most useful advantage of this technique for us is to get adjoint variables P and Q directly. I mean, we have a chance to solve P and Q without using any extra derivation. So these equations are calculated from derivative of Lagrangian with respect to u, that setting to 0 actually. Since we have two different control variables, we have two different gradient equation actually. Also, the coefficients, the coefficients of the Runge-Kutta scheme for adjoint variables have some relation between the coefficients of the state equations. I'm going to show you a similar optimality system for pure jump model also. So we omit here W term. And this is the discrete form of our scheme for which one? This is the pure jump model. They're actually similar to each other, but just we omitted the WT term. So it is a simplified version actually. Here we have optimality system pk plus 1 is equal to pk and so on. Also we have intermediate values calculated here. Discrete state is also given here, and we have the gradient equation satisfying the following relations. The coefficients satisfy the following relations. Now I want to talk about some numerical results. Here, okay, we have discrete scheme. Our problem is discretized by using Runge-Kutta method. We have optimality system, so we are ready to solve a stochastic control numerically. There is one more thing. We face taking expected value of the test function, so that we use Monte Carlo simulation for such values. Monte Carlo simulation is a technique. It is widely used in finance, engineering, physics, and other fields. This technique is based on taking the average value of the integration over domain actually. Here, integration is changed as summation, and we take the average of this summation by dividing the number of samples we use in our calculations. Of course, after getting optimality conditions and using Runge-Kutta scheme, we have to talk about the Runge-Kutta coefficients. Actually, one may choose Runge-Kutta coefficients to get a higher convergence, higher order convergence. For example, if you set only some conditions, one condition as in our case, then you have a low order convergence. But if you want to get a higher order convergence, you can deal with Taylor series expansions and get the relations between coefficients. But now we just consider a low order convergence at the beginning in our case. We use 5,000 samples. Also, we choose delta T as 1/100, and we use a simple Bachelor table to get our coefficients, Runge-Kutta coefficients. By using this Bachelor table, this is the scheme of our this here we this is the pure jump model. There is no WT term. So we consider some examples to compare the effect of risk coefficients. When we get a big risk coefficient, then our control is getting larger. If it is smaller, then it is smaller. So it is directly dependent on the value of the risk coefficient. So the left-hand side graph is a comparison for a control variable, and the right-hand side is for the state variable by using different values for risk coefficient. In example 2, now we consider a stochastic term also. And in this case, we have 3 different tables, Bachelor tables, because we have a deterministic case effect, a stochastic effect, and a jump effect. Let me show you the scheme by using this Bachelor table. We have this result after using the values denoted, defined in the Bachelor table. So we use the desired state y as 1, and we have control and state variable solutions. Here we choose R as 0.01 and sigma as 0.5. Again, we have a lower risk rate yields a small control variable in this example also. Again, we present some state variable solutions for different risk values. So, as an outlook, this study may be extended to other complex differential equations, for example, partial differential equations, or one may be interested in getting a higher convergence rate so that Runge-Kutta scheme can be analyzed for optimal control problem and get the order conditions. Actually, I think this is the end of my speech. I would like to answer your questions if you have.
Okay, thank you for the great talk. We
okay, thank you so much.
For you. So let's see if we have any questions for you here. Do you have any questions for our speaker? No?
Thank you, Professor.
You're welcome. Thank you.
So